Getting robots back on track. When deployed in real-world scenarios, robots and vehicles are likely to face dangerous or unexpected situations that might impact aerodynamics. In such scenarios, the operator might lose control, leading to potentially worldwide consequences. This is what happened when the Ever Given ship blocked the Suez Canal. When the ship got too close to the edge at high speed, the Bernoulli perturbations attracted it on both sides, creating an instability. In this work, we propose FLARE, Fast Learning Based Adaptation for Immediate Recovery. FLARE is an automated online system that allows drivers to regain the operability of a system impacted by critical perturbations. Importantly, FLARE is not a controller, but a hierarchical layer that can be put on top of any base controller. As an example, we consider a perturbation that combines a loss of traction on the right side and a slippage naturally occurring in a wooden ramp. On the right side, we show a driver impacted by this perturbation, and on the left, the same driver on the same system, but with FLARE. On the right, we can see that the driver is manually compensating for this perturbation, while on the left, FLARE does so automatically. To do so, FLARE learns a model of the effect of the perturbation fully online using only onboard sensors and compute. The combination of a loss of traction and slippage makes it really hard to turn at the top of the ramp. With FLARE, the driver drives more smoothly than without FLARE and gets stuck less often, leading it to complete the circuit faster. FLARE is designed to work fully online using only data from the onboard sensors of the robot. It first acquires these data points and constitutes a dataset. Using this dataset, FLARE learns a model of the effect of the perturbations. Once learned, the model is deployed on the onboard computer. FLARE also continuously detects changes in the perturbations and is able to reset its model. All those steps occur in less than 2 seconds, multiple times per minute, and fully online on the robot. Importantly, the strength of FLARE is that it does not replace the existing controller, but enhances it by acting as a hierarchical controller. To illustrate the learning speed of FLARE, we apply a simulated loss of traction on the right track of the robot. At first, both drivers are impacted by the perturbation. Now FLARE has learned. The driver with FLARE is now following the track as if no perturbation was applied. This allows the driver with FLARE to finish the circuit long before the driver without FLARE. When later getting back to this part of the circuit, the driver with FLARE successfully navigates it. While the driver without FLARE is getting stuck and takes a significant amount of time to complete it. We demonstrate this quick learning ability on more complex perturbations, such as this wind perturbation. Here the robot is deviated by the simulated wind coming from the bottom left corner of the room. This perturbation is highly counterintuitive for human drivers, making it difficult to compensate manually. FLARE learns the effect of the wind and counteracts it, allowing the user to turn smoothly again. An additional strength of FLARE is that the learned model is interpretable for human drivers and allows introspection. It takes the form of a Taylor expansion, whose coefficients can help understand the perturbation applied to the system. We illustrate this introspection ability in this task that simulates the Bernoulli perturbation in a canal. The robot plays the role of a ship, and the treadmill simulates the canal. The strength of the Bernoulli perturbation is proportional to the distance to the edge of the canal. On the right, the polynomial prediction of FLARE shows the strength of the perturbation with respect to the robot's position. The green dot indicates the current position of the robot. In the paper, we evaluate FLARE across a wide range of circuits and perturbations. We demonstrate that FLARE reduces the impact of external perturbations, which allows the operator to recover 82% of the operability and 80% of the completion time of the unperturbed robot in our experiments. In summary, we propose FLARE, or Fast Learning Based Adaptation for Immediate Recovery. Flare is an automated online system that allows drivers to regain the operability of a system impacted by perturbations in a few seconds. Thank you very much.